Uh, we shall continue this webinar series maybe in online or offline mode in future depending upon the situation. I want to thank all my departmental colleagues and students for their active support, always for the academic excellence of the department. Now, without further delay, may I request Dr. Tapati Dotto to kindly introduce Ruhul, his student. So over to you, Tapati.
So thanks, Indra, and good afternoon to all of you. And thanks very much for joining. And I thank Ruhul also for agreeing to share his work with all of us in the department here. I want to say that for me, it is a privilege to have a student like Ruhul. He has he is of just the right disposition or temperament that I would love to see in myself. You know, quiet, dignified, serious, but with a very, very subtle sense of humor. And of course, an avid love for physics. Ruhul has joined our department. I think Ruhul, as a PhD scholar, it would be 2018 or 19, maybe. Ruhul can clarify here. And to introduce Ruhul, I don't really know how to do that because he's our student, all of our students. And to the UG and PG students, I think you could just say he's your dada. And there was a time before COVID when you would see him in the laboratory as you would then notice other PhD scholars. COVID has changed many things, including that, and I hope to see that we will be seeing the more active participation of our PhD scholars in the daily running of the department sometime soon. Ruhul comes from a village in Malda. He did his Madhyamik and Ucha Madhyamik from there and did his Ph.D, then came over to Kolkata and did his B.Sc from Bangobashi College. From there, he went on to do his MSc from IIT Delhi and from there to St. Xavier's College. He has an avid interest in simulations, computer programming, modeling, has a great acumen for mathematical physics and statistical mechanics. This is all that I have discovered. There could be much more, you know. And I think Ruhul will be sharing some aspects of his work, which he has been doing. So over to you, Ruhul, and all the best for your talk. Indra, that's
Thank
it,
you.
I think.
Thank you, Tapati. Thank you. Now, Ruhul, the stage is yours. Please start your talk.
Thank you, sir. Thank you, ma'am. Okay. Can you see my screen?
Yes. Just make it larger. Yes.
Okay. So today I'll be talking about topology and geometry of fracture networks and how to use them to characterize the networks. So in our everyday life, we see fractures everywhere surrounding us. It the mud field, mud cracked due to desiccation, or it could be in the large stone which is cracked due to mechanical stress, or it could be in the paint that we hang in our wall, or it could be in the glass of our window. So if you notice carefully, all the cracks are not same. Some cracks are more like hexagonal, some are like triangles, a bit elongated, which are and some are not elongated, some are more like squares. So our eye can perceive those differences, we can differentiate and the other properties. But in mathematics, how can we distinguish them? So people try to distinguish these polygons or the fracture networks using their topological properties. So if you say that these black lines are the fractures or the crack lines, and if two or more crack lines meet at a point, they form a node. And if they form a loop, if the crack lines form a loop, then they make or they create a polygon. And for a node, for a particular node, suppose that the cursor, the node I'm pointing by the cursor, if all the polygons surrounding this node uses this node as their vertices, then we will call this node as regular node. And if not, you can see in the right side that this node is not shared by this polygon as its vertex, but these two polygons have this node as their vertices. So this node is not regular node. So this is irregular node. Say the basic definition I am going to. And another thing, the degree, how many polygons sharing a particular node assigned to this node as its n value. And for a particular polygon, if you say this polygon, how many edges this polygon has, it's defined. So as this polygon has 4 edges or 4 V is 4 here, and this node is shared by 2 polygons, so its n value is 2. So in a mosaic, there could be regular or irregular both type of nodes. So you can see the blue ones are the regular nodes and the red ones are irregular nodes. So the mosaic is characterized by a variable which is called characterized by P, which is called the regularity index of the mosaic, and it is defined by the total number of regular nodes by total number of nodes. So for this example, it has 4 nodes. Say it has 4 nodes. These two blue nodes are regular nodes. So its regularity index P is 2 over 4. This is 0.5. Okay. So in topology, the NV uh, they follow a certain rule. So for a convex mosaic, for a convex mosaic, the NV, the average number of N and average number of V, it is followed by this equation: P plus 1 over N plus 2 by V equals 1. Here uh, P is the regularity index I defined earlier, and N is the average number of N for each nodes, and V is the average number of V if you consider all the polygons. Okay. So if we see clearly that this P can vary from 0 to 1. So for pure regular, if all the nodes are regular in this mosaic, so this P will be 1. And if all the nodes are irregular, so P value will be 0, 0 over 4, so 0. Therefore, if we put P equals 0 in this equation, it will define this line, this curve. And if we put P equals 1 for pure regular node, it will, for pure regular mosaic, it will give you this curve. So this two curve defines the boundary of this region, two boundaries of the region. And for a polygon, there must be at least 3 vertices. So V must be greater than or equals to 3, which defines the third boundary. And it can be easily proven that V must be less than 2 times N. So this defines the fourth boundary. So for a convex mosaic, the NB value must lie within this mathematically allowed region. For example, if we take the big layer mosaic, for which the n value, each node, this is a node, this is irregular node because I have shown you in the previous slide. This is the irregular node, and its n value is 2. It's shared by 2 polygons, and its v value, each polygons have 4 vertices, so its average v is also 4, and its average n is also 2. Therefore, it lies or it sits on the 2 for this point. For hexagonal mosaic or hexagonal lattice, you can say, each node is shared with 3 polygons, and each polygons have 4 vertices or 6 vertices. So this mosaic will sit on this point 3 6. And for the square lattice, is n and v both are 4. This node is shared by 4 polygons, and each polygon has 4 vertices. Okay. Then we took some real images and processed them to find the NV values. First, we did what? We extract the binary image from the real image, and then we extract the skeleton of the crack lines. Here is the white line is the actual crack. So we have to find this crack skeleton. So figure C shows the skeleton, and then we detected the vertices. Figure D shows the vertices. This black point shows the vertices, and these are the polygons. And then we counted N and V for each polygons and these nodes, and then draw them on the NV plane to see how they are scattered in this space, NV space. We did the same process for some mathematical cracks to compare them with the real cracks. So we took 3 mathematical cracks, namely the Gilberttessellations, Tessellation, and iterative cell divisions. So Gilbert for Gilberttessellation, we have to tessellate the entire space by few random points, which are known as the seeds. So from the seeds, crack in different orientations or random orientations begin to grow, and they grow until they collide with another crack, and they form the entire tessellations like this. And we can also put constraint on the orientation, that if I want, I can only allow these cracks to grow only a certain directions, and therefore we can get the variations of the tessellations. So, for example, the first figure shows the Gilbert tessellation for random orientations. The second one, we have only allowed the crack propagation along the x-axis and y-axis, and the third one is allowed within the region plus minus 10 degrees of the axis, x and y. And the fourth one, only 0, 45 degree and 90 degree. Those crack orientations are allowed. So for all the 4 cracks, the mechanism is same, but due to various constraints, their mosaics are different. And for the Voronoi tessellation, we tessellate the entire space using some random seeds, and the tessellation is made by, you see that 2 seeds. The blue ones are the seeds which creates these Voronoi tessellations. So if we join a line, those 2 neighboring seeds, and bisect this line perpendicularly, then for all the lines, if you join, then the perpendicular bisectors will form the Voronoi tessellation. And the Voronoi region corresponding to a particular seed, all the regions within the Voronoi region, all the points within this Voronoi region, its distance is closer than any other point, any other seeds. So this forms the regions are formed with the closest points. And the third one is the iterative cell division. In this process, we take a blank box, you can say, and divide it in two parts with a random line and get two different polygons. And then again, we divide these two new polygons with two random lines to get four new polygons, and we iteratively do this process, and uh, as we and add more and more polygons, and hence we tessellate the entire space. So we calculate NV for those real cracks by image processing and the mathematical cracks, and plotted them in this NV plane. So you can see that the points are crowded in this region mode. This line is known as Platonic attractor. So they are more attracted in this region, and some of the points, the Borneo mosaic, and the mud crack also are in this region, which is known as the Borneo attractor. You can clearly see that these NV values cannot differentiate the fracture networks properly. For example, the cell division and Gilberttessellations, these two mosaics are of different mechanism. Their shapes, their shape are different. You can see that the iterative cell divisions are more bit elongated. The polygons of the iterative cell divisions are a little bit elongated than Gilbert one, but their n and v values are both same. Both have n equals 2 and v equals 4. So for both of them, the NV lies on this point. Therefore, it cannot distinguish these two fracture networks. So we have to consider their geometric properties also to distinguish them properly, to classify them properly. So we took angular defect and well-known isoparametric ratio. This term isoparametric ratio is well-known in mathematics. So angular defect is defined by this statement, this equation. So this is actually, angular defect is actually defines or states, or this is an index of how much a polygon deviates from its regular form. So for example, if you take a square, its all angles are 90 degrees or pi by 2. So this term, theta I minus v is the number of vertices or edges, minus 2 by v. If we calculate this one, pi by 2 minus 4 minus 2 by 4, this is 1 by 2 into pi. So pi by 2 minus pi by 2, this is 0. So for all the regular polygons, this term is always 0, and hence d is equals to 1. As the polygon deviates from its regular form, so theta 1 is less than 90 degree, theta 2 is greater than 90 degree. So this term is non-zero. Theta I minus this term is non-zero, and hence the sum is always positive. Therefore, d is always will be less than 1. So as the polygon deviates more and more from its regular one, it tends to 0 more and more. And theoretically, this value of d can be from 0 to 1. And the isoparametric ratio, this is defined by 4 pi a over L square, where a is the area of the polygon and L is the perimeter. So for circle, this is perfect one. This is pi r square, and this is 2 pi r whole square. Therefore, this is 1. But as this shape of the polygon deviates from deviates from circular form, it tends to decreases from 1. So for example, if we take a square, you can easily calculate the lambda equals pi by 4, which is less than 1. Okay, and as it elongates, the shape of this polygon elongates more and more, it tends to 0 more and more. So the value of lambda varies from 0 to 1. Then if we calculate the d lambda, and we have already calculated n and v and plot them in 3D, we can see that this can clearly distinguish such fractures, the Gilbert and cell divisions. We have previously shown that we have previously seen that these two are in the same point in NV space, but in NVD space, the green one is the Borneo cell division and the blue one is the Gilbert mosaic. They are on two different positions, so D can clearly distinguish them. And in the lambda space also, we can see that they are in different positions, and not only them, all other mosaics are scattered uniformly. So this NVD and NV lambda are better choice to if you want to classify or distinguish or characterize the mosaics or the fracture networks. So we have previously seen that in the NV plane, NV space, the points are either crowded around the Platonic region or the Borneo region, Borneo attractor. So a natural curiosity arises that is there any system or dynamic system which begins from this region and travels up to this region or vice versa. There is luckily some systems, for example, the columnar joints, which are formed due to the cooling of molten lava. The surface of the molten lava cracks due to cooling, cracks randomly. And with time, it propagates vertically and changes the shape of the columns in such a way that they are not random now. You can see that they are more bit like Voronoi polygons. So it starts from random polygons or random mosaics, which is a kind of you can say Gilbert one is a random mosaic, which situates in the Platonic region, and it ends into the Voronoi mosaics, which is in the Voronoi attractor. So this is the perfect candidate for us if you want to track the NB or NBT, NB lambda, how they changes over time. So to understand how the shape of the columns changes, we have to understand the thermal profile of the columnar joints also. So this is a vertical cross section of columnar joint. So this A, B, C are basically the columnar joints or the cooling lavas, and this gray line you can see this is the crack space, and this is filled by air, and the heat flows through the air in a convective way, and the heat in this medium or in this column or in this lava, they transport in a conductive way. So the convective way is faster than conductive way, and therefore the edges are more cool. They are cooler than the center of the columns. The dashed line shows the isothermal curves. You can see here the temperature. Here the temperature is higher. You can see in this region. So if you say that this is 100 degrees Celsius, sorry, this is 100 degrees Celsius. So as the, this is cooling from the surface. So this, if this is 100 degrees Celsius, it could be 150, it could be 200. So in this horizontal plane, if we go from here to here, it will be 100 degrees Celsius, it will be 150, it will be 200. So there is a thermal gradient. And also one thing we have to consider that the temperature of the the temperature at the center of the thick column is higher than the temperature of the thin column. Therefore, the temperature gradient along this direction is higher than the temperature gradient along this direction. So the crack tip, this crack is propagating, you see, with time. So this crack tip will propagate or advance in such a direction so that the maximum stress is released. So it will propagate in the maximum thermal stress region. So this new crack will advance in this direction. We have simulated this the columnar joint using this same mechanism I have discussed in the previous slide. So at the first, the top of the surface, we have taken random cracks, and Gilbert is one kind of random cracks, and this and we have moved the nodes according to the principle in the thicker region. Each nodes try to move along the thicker region, and and they finally stops, matures uh, after, you can say, for okay, I have to say this one. So this is the vertical cross section of the columnar joints. So these polygons are actually the columns. So and the black dots represents the centroid of the columns. So this red dot is the node or vertex of the system, and it will try to move in that direction in which the distance from this in that this node will try to move in the direction of the node or of the centroid, which is in the maximum distance from this node. So basically, this red node will try to move in the thicker or the thicker polygon. You can see clearly from this region, from this simulation, that they are moving using this principle. So you can see that they started from random crack and they finally measured with Voronoi-like patterns. These are the 3D versions of those simulations. So you can see clearly here that it started from random crack and measured with Voronoi crack. And this one is the how the shape of one particular column is changing over time. You can see its number of vertices were 4, and it matured as its number of vertices with 6. So in the NVD space, the NVD value changes according to this curves. So they decrease in the first, and then they increases to a certain point. So they started from 2,4, this point 2,4 in NV plane. They started from 2,4, and they matured to this point, which is 3,6. Okay, one thing here is to notice that the area distribution of the area is not changing much over time. You can see that the blue one is when we begin the simulation t equals 0, and the green when the crack matures. So they are grossly same, but the angular distribution of the polygons or the columns changing much. The, at the beginning, the blue one, this one, the peak of the angles were at around 90 degrees, no, sorry, 60 degrees. And as time increases, the peak shifted towards 120 degrees. So basically, the area distribution is not changing, but shape of the columns are changing. So one thing we have to consider also that how the energy of the system is changing over time. So any dynamical system will want to change such that its overall energy tends to minimum. So we can divide this system of the entire energy in two parts, namely the elastic energy, which depends on the volume, or we can say this is the volumetric energy of the system, and another one was the fracture energy, where L is the total crack length. If you see these black lines at the crack, so the total crack length is, if you sum the length, all the length or the perimeter of the polygons, will find the total crack length. And in the vertical direction, the crack is propagating or moving in the vertical direction. So if we multiply the vertical distance digit, then in this time step we'll find how much new crack or new crack area has been created. This is the L multiplied by digit. And if we multiply this with the term eta, which is fracture energy per unit area, so this total term will give us the fracture energy due to this advancement of the crack. So the energy functional, the volumetric energy plus this fracture energy must tends to some minimum value as the system evolves. So one thing we have noticed earlier that the area distribution is not changing much, but the angular distribution or the shape of the columns are changing. So there must be a relation between the shape parameter, that is lambda, with this energy functional, and we proposed a relation between them, which is alpha to the power minus beta. Alpha and beta are the constants, some constants we have to find by some mathematical fittings. So we have calculated these energies using our equation, that is alpha lambda to the power minus beta, and the previous energy equation, that is this one. So you can see clearly that over time they are minimizing. They tends to a minimum, certain minimum as they matures, and the both energies agree. The curve of these two energy agrees with a certain degree. Therefore, the shape parameter lambda, we can use it to define the change in energy about the energy functional. So this was our main work in these two papers. Here are the references: the Combinatorial topology and geometry fracture network. It has been accepted in PRE, and the second one is the columnar joint one. It has been accepted in Langmuir. It is not published yet, but they had accepted this one.
Okay, thank you, Ruhul. Questions? Anyone having questions? Acha, Ruhul, can you apply these things to the network problems? This your study that you have done. Can you apply the network formalism in this particular type of problems? But this is just a naive question. Just I wanted to understand these things. Is it studied already?
In network problem, okay, the NV thing, the N and V, they are the topological properties. They can be used in network analysis or network problems, but the geometry is purely for the mosaics one. So if you apply this one, you can apply the topological properties. I said the N and B properties. They can be used in network.
Also, there must be some experiments on this that you have matched with your simulation results, right?
Yeah, experiment in so okay, experiments. All the fractures were experimental cracks.
Right,
So
right.
real images were the experimental fractures, and about the columnar joint is happens in nature already. But some experiments also shows the like cornstarch. They
Right.
and they desiccates. They finally they form columns like uh, the hexagonal like pattern. So this happens in experiment also.
In fact, in your group, they are doing experiments also, that I know, right?
Yeah.
The group members are doing experiments also in this regard. Anyone having any question, please feel free to ask Ruhul.
Ruhul, so may I ask a question?
Yes,
Yeah.
Ashadul, please go ahead.
Ruhul, can magnetic field affect those crack patterns?
Oh, yeah, surely, sure. They can affect. We have not considered here, but sure, they can affect.
So, Earth's magnetic field can be different in different places. So, if you carried out the same experiment in different place, so you will get different result.
Okay, but Earth's magnet is not that much strong to affect these systems. Uh, and another thing that the magnetic field will affect not all the substances, in particular substances which reacts with magnet or which constitutes of ferrous materials. You can say they they actually if they are affected by the
So, you need
magnetic field.
ferromagnetic materials.
Yeah. So
I think that yes.
in the experiments, Samilda maybe or in our groups, um, some scholars are doing or already have done the magnetic effect on crack also.
Yeah, Ruhul, I think that temperature has got a greater effect on the cracks compared to the magnetic fields, right? If
Yeah,
you
for
vary
the
temperatures.
cooling lava, the cooling lava scene, yes, the temperature is the yeah, the main cause. But for the mud crack, this is the desiccation moisture. For the cornstarch, you can say the moisture is also the main reason.
Any questions, any comments, please feel free. Okay, I think that since there is no questions, and I thank Ruhul and all my colleagues and students, those who are present today, I think this forum we should continue. That students, their work, not only the PhD students but undergraduate students, they are doing fantastic projects because this time we have seen very good projects they have submitted and they have defended. So we can ask the students also to come and participate if they want. They can give lecture on their work. So I think that this kind of activity we are going to continue in the department. Thank you for your presence today. So thank you, Ashadul, because Ashadul is the prime factor or energy to hold this kind of seminars. So thank you, Ashadul, and all my colleagues and students, especially Ruhul today. Thank you for your work. All the best wishes for you for your future. Thank you very much.